In previous lectures, we've talked about how the internal energy of a system is equal to the total energy of that system. So our E is equal to Q plus W, Q being energy in the form of released heat, and W being in the form of work. But as chemists, we often only want to look at heat, not work. So a lot of the time, we're really going to be concerned about this Q value, not so much about the W value. So in these instances, we have a special value that allows us to focus on that Q. And that value is what we call enthalpy. And that enthalpy is often called delta H. And the definition of that is the heat of a system at constant pressure. And that's really key, that the pressure is constant. Think back to our previous lecture with bomb calorimetry. So because with bomb calorimetry, our pressure isn't constant, the volume is constant, but the pressure is changing, that means that that method isn't really going to be that great for solving for enthalpy. So when we're doing enthalpy calculations, we're going to need to use methods other than bomb calorimetry, and we're going to be talking about that in the next couple of lectures. So another way that you can write this is that delta H is equal to Q, so Q is heat, remember, with a lowercase, or not a lowercase, a subscript P. So that means that the Q, the heat, is at constant pressure. And if you're somebody who really likes to know where your equations come from, the textbook has a really great derivation of this. I'm not going to go through it in detail in this video, but again, if you're interested or really enjoy math, go ahead and take a look at that. So some important information about this delta H value is that when delta H is positive, so we have positive delta H, that means that energy flows into the system. So the system is gaining energy. And in this context, we're specifically talking about energy in the form of heat. And when delta H is positive, we call that endothermic. Alternatively, when delta H is negative, energy is flowing out of the system. And we call that exothermic. So it's a little bit hard to imagine what this really means and kind of like put it into, I guess, what you could call real world context. So one of the ways you can think about this is if we have an endothermic reaction or an endothermic process, that process is going to be cold to the touch because the energy is flowing out of our hand and into whatever that process is. So an endothermic process to us will feel cold because the energy is flowing out of our hand and into the system. And an exothermic process will feel warm to the touch because the system is releasing energy, and our bodies will pick up on that and it'll feel warm to us. So for example, let's say that we have an ice cube in the palm of our hand and we can watch it melting. So we know that ice cube is going to feel really cold, and that's because it's taking in that energy from our hand and it's using that energy to melt. So the energy is flowing out of our body into the ice cube, which causes it to change from the solid to liquid form. So that would be an example of a physical process being endothermic. Chemical processes can also be endo or exothermic. That's mostly what we're going to be talking about in this class. So for chemical reactions, I'm going to abbreviate that as chem RXNs. So for chemical reactions, just kind of like some basic background knowledge, breaking bonds is going to require energy input. While forming bonds will release energy. So when a reaction requires more energy to break the bonds than it can release, it is endothermic. And when a reaction gives off more energy than was required to break the bonds, that reaction is going to be exothermic. And I'll show what that actually looks like graphically. And I'm sorry in advance for my terrible drawing skills, but hopefully this will help you visualize the difference between these two types of reactions. So I'll draw two graphs here. And this will be our graph for our endothermic reaction. And then this one will be a graph for our exothermic reaction. And then on our axes, we'll have time. On our x-axis, so our 0 point here is going to be the start of the reaction. And then on the right side of the graph, that'll be the end of reaction. And then on our y-axis, we're going to have the amount of energy in the system and this is going to use units of either joules, kilojoules, something along those lines. So I'm just going to say in this example, we'll use kilojoules. And then for time, we'll use seconds. So in an endothermic reaction, at the start of our reaction, we know, and we've talked about this already in previous classes, in order to get a reaction started, we need some input of energy. And then this is going to be the energy that's required to break bonds. And then as we form bonds, we're going to release some energy. And then when the reaction's over, it's going to even out. So this value here, that's going to be the energy that is required to break the chemical bonds. So that's going to be our energy input. And then this amount here is going to be the energy that's given off when new bonds are formed. So energy released when new bonds are formed. So that's our output. So notice we still have, this difference here. So we have a difference from how much energy we had when we started. We have more energy in the system at the end of the reaction. So you have more energy at the end of the reaction. That means that this reaction was endothermic because it took in a net gain in energy. So how does this compare to an exothermic reaction? Let's say that we start at about the same place, and just imagine that our axes are the same, so this one's also going to be energy in kilojoules, this one's going to be time in seconds. So for an exothermic reaction, even though energy is being given off, we still need some kind of energy input in order to get that reaction started. So we're going to have some kind of energy input as we break bonds, and then as we form bonds, energy is going to be released. So again, we have our input. And then notice here how we have a much larger output as bonds were formed. And what that does is it shows that we have less energy at the end of the reaction than we did when we started. So that's going to be a net loss of energy. So basically, an exothermic reaction releases more energy than it puts in. So to summarize, an endothermic reaction has a greater energy input than energy output. So you can see this, this value here is larger than this value, where an exothermic reaction has a larger output than input. So whichever one's larger, that's going to determine whether it's an endo or exothermic reaction.